Okay, James, so for next time, we're going to do two theorems that have to do with the geometric mean. So you'll need this note sheet that we've already started. And just to recap, we can take an arithmetic mean, which is what you've already learned for many years as the average. So it's the sum of the numbers divided by the number of numbers. Then we have the geometric mean, which in your case, for geometry purposes, we're just doing the geometric mean of two numbers. So it's kind of the numbers that come between two numbers when we're multiplying them. And the way we do that is the product of the two numbers and then take the square root of it. So we did a little bit of that last time, but we're going to pop on down here towards the bottom that we didn't do and talk about how this applies to two theorems in geometry. So when we have a right triangle, we can actually split it into two similar triangles and draw the altitude. So remember that an altitude goes from the vertex, and in this case we're going to specifically look at the altitude from the vertex of the right angle to the other side. So we drew it, and then it's perpendicular to the other side. That makes it the altitude. Okay, so if you can look at that then, this is the same triangle drawn, but we've labeled a couple of the sides. So C and D are these two smaller segments that make up this whole other entire side, F. And then E is the altitude. Don't worry right now for A and B, the legs. Those will come on the back of this sheet. But right now we're concerned with the relationship between the altitude that we just drew and this opposite side. So what the altitude theorem says is that the altitude, oh, James, that's you. The altitude, which in this case is E, is equal to the geometric mean of the two segments making up the opposite side. So right now you're probably like, what in the world does that mean? Well, the two segments making up the opposite side are C and D. And a property of right triangles then is that this altitude, E, is equal to the geometric mean, which we know is the square root of the two segments making up the opposite side, which would be C times D. So let that sink in for a second, but that is the formula for it. So you're essentially multiplying these two and then taking the square root, and you wind up getting the altitude. All right. So on the back, we're going to do one more theorem, and then we're going to put all of these together in a couple of examples. So this is the leg theorem. Oops, sorry, let me make it straight. So the leg theorem says something a bit different. The leg theorem says that there is a relationship between the two triangles that are formed. So there's this triangle that I'm going to outline in pink that's formed by the altitude of the big right triangle, and then we'll do green for another one. And then there's this triangle over here. So hopefully you can see those. Those are also two right triangles. And then there's going to be a relationship between the altitude and these two sides of the right triangle. So what this one is going to say is that because we draw this altitude, it makes these right triangles have this special property. And what the special property is that this side, the hypotenuse of one of the smaller triangles, so a squared equals the product of the shorter side, the shorter leg of this right triangle, to the entire hypotenuse of our original triangle. So C times F. That's kind of confusing, but this is the leg of small right triangle times the hypotenuse of original triangle. And then if we want to find A, we can take the square root. So in other words, the hypotenuse of one of the smaller triangles formed is equal to the geometric mean. So if we square rooted both sides here, that's where this is coming from. The geometric mean of the leg of the triangle times the hypotenuse of the original one formed. So that's a little bit different than the relationship we had on the front side where we were doing the altitude theorem. So it really doesn't have anything to do with E, the altitude, except that E is the height of the two triangles formed. So you have to have it perpendicular to the opposite side for this to work out. So if we had drawn in something like this and split the two triangles, A would not be equal to this distance times F, and taking the geometric mean of that. So the altitude makes this property happen. So in a similar manner, you could also look at the green triangle, and the same relationship happens. This hypotenuse of the smaller triangle formed, the green triangle, is equal to the geometric mean of its segment over here, D, times the original hypotenuse of the original right triangle, D times F, so geometric mean. So both of those properties. Okay, so let's put that together. We're going to do more practice with this next time, but let's put that together in an example problem. All right, so in this example problem, we see that there's a big right triangle, and then we're given a couple of the side lengths, and we have to find the rest of them. So the first thing I'm going to do is look at, okay, I have the hypotenuse of the original triangle, the big triangle, and then I also have this smaller segment off of this kind of green triangle formed. I'll outline that for you. So right now I have nothing to do with the altitude, so I think that what I'm going to use is the leg theorem. That's about the hypotenuse of this smaller triangle formed. It was kind of like the B up here. So this Y, the hypotenuse of the new triangle formed, would be equal to the geometric mean of its leg, that's why it's called the leg theorem, and the original hypotenuse of the big right triangle, 9. So that gives us the square root of 27, which we all know is 3 root 3. Okay, so if this is 3 root 3, how in the world can I find this length here? Well, we can use our handy-dandy Pythagorean theorem for that. Right now you cannot do the altitude theorem. That was the first theorem we covered today because we don't have x over here. Oh, actually we could. Let's do it that way. You could do it either way. So we could use the Pythagorean theorem. Sorry for messing with your head. But we could also say, okay, if this side is 3, and again, James, these are not drawn to scale, and this whole thing is 9, then x must be 6. That would be an easier way. Sorry, I didn't see that a second ago. But then we would know, based on the altitude theorem, that the altitude, z, is equal to the geometric mean of the two segments that it splits the hypotenuse into, so 6 and 3. That gives us the square root of 18 is equal to z, and we all know that's 3 root 2. All right, and last but not least, we need to find W. So we know using the leg theorem, we can do something similar to what we did over here. So the hypotenuse of that small triangle formed, the pink triangle, is equal to the geometric mean of 6, its leg, to the original hypotenuse length. That gives us the square root of 54, which is 3 root 6. So we finished that triangle then. So these two, y and w, we used the leg theorem for, which says that the hypotenuse of the smaller triangle is equal to the geometric mean of its leg and the original hypotenuse, 9. And then for this one, we use the altitude theorem, which, just to recap, says that the altitude of the big right triangle is equal to the geometric mean of the two segments it splits the hypotenuse into. All right, let's do one more. Oh, my paper bled through a little, so ignore this stuff down here. Okay, so in this right triangle, we have the altitude given to us. So let's start with the altitude theorem, using that. So this works just like algebra, and we can actually plug in. So we know that normally the altitude is equal to the geometric mean of the two segments it splits the hypotenuse into. So I'm going to set up my algebraic equation. So instead of solving for the altitude, I'm solving for one of the segments, the square root of 5 times y. So that's geometric mean of these two segments. Then we're going to solve that. So to get rid of the square root, I'm going to square both sides. Then divide by 5, and I get y is 20. Hopefully you're with me so far. So from there, then I have to find the hypotenuse of both this small little right triangle, x, and of this other smaller right triangle. So we're going to have to do it twice. So we're going to use the leg theorem. And let's go for z first. So we know that z is equal to the geometric mean of the leg of that smaller right triangle, which is y, so 20, times the entire hypotenuse of our original right triangle, which if we add those together, we know is 25. Okay, so I don't have my calculator with me, so I'm going to actually do this in my head by splitting these into root 20 times root 25. That'll make my life a little easier. So this one, 4 goes into, it becomes 2 root 5 times 5, which is 10 root 5 for z. All right, and let's do that one more time to find x. So again, the hypotenuse of the small little triangle formed, x, is equal to the geometric mean of its leg, 5, to the entire hypotenuse of the original big right triangle. Again, I don't want to do that out and then have to take the square root of it, so I'm going to split it. So it becomes root 5 times root 25. This becomes 5, so my final answer for x is 5 root 5. And there we've solved for x, y, and z. Hopefully that wasn't too confusing. They're a little bit easy to mix up, but the altitude theorem is obviously with the altitude equal to the geometric mean of the two sides. It really has nothing to do with the two small triangles. And the leg theorem is all about the small triangles and finding the hypotenuse of those. So I will see you next time.